right, so last time we talked about sampling, right? So not Costco samples, but like sampling of like how we pull this information from a population, right? So we're gonna move that in. We then talked about the central limit theorem, right? So remember the central limit theorem is like the holy grail, doing statistics is like, if we can get, what was so cool about the central limit theorem? Someone give me a quick, like, what distribution did we care about it? Because it makes sense.
It's a normalized distribution. It a bunch of samples that form a normalized distribution.
Yeah, it creates a normal distribution, which is like cool. Like we can basically take this means of the sample means, or like the sample means, take many samples, and we can actually create this this normal curve from the central limit theorem. And because we can do this, we're like, perfect. We caught a normal distribution. We caught a Gaussian. We can now basically do whatever we want with it, knowing the mathematics from it. And that's why the central limit theorem is so important. So yeah, that's what we did last time. So today we're going to talk about confidence intervals. And so confidence intervals will basically say, hey, if we got a new, sample, how do we know if it's actually representative of, the real population, right? So what if you get a bunch of, like they collect a bunch of weirdos and you're like, your samples, like maybe these people are always, or like subjects or whatever it is, maybe you just happen across like a random like group. For example, with the Titanic's population or ages in the Titanic data, we saw that most people are around 28, 30 years old, but there were some people who were older, like in their 80s, for example, or I think 60s or 80s or something. What if we accidentally sampled and only got those people on the edge, the very untypical, part of the population? Well, we don't really know. So the idea with the confidence intervals is we can say, based on the sample we pulled up, how confident can we say, well, basically have a level of saying how confident, how our sample mean relates to what we think the population is. We still don't ever know, but we can at least get an idea of how close we think we could be. Okay. So let's go into confidence intervals. What is this? Oh, central limit. You don't need this guy. All right, confidence intervals. So I'm going to clear this guy so we can start from the beginning. I was playing around with some stuff, so let's minimize this just to make things easy. There we go. So confidence intervals. So basically this is taking our sample and we don't actually know what the population is like. So we're just kind of pulling this information saying, hey, we got a sample. What can we say about it in regards to the population? So if you remember, if we can take our sample, calculate the mean, calculate the average, and we can say that's probably around the population average, but how confident can we say? So kind of quickly before we kind of talk about like how confident it is, does anyone got an idea? Well, I'm going to pose you a question. Let's say I survey 15 people and I ask them what your age, like what's their age, right? And so I ask those 15 people, I get a number. And then let's say Christine instead asks 50 people, right? And she asks, what's their age? And then let's say we have Edward, right? He asked 1,000 people what their age is. Which person do you think has the best approximate to the true population? Just based on like what we just said.
The one with the higher sample count.
Yeah, right. You can get a feel for that, right? Like you get a higher number of things. Let's go to another scenario. Let's say I pull up a sample, right? I pull, 100 people, right? And they're all very, very close together. And then there's one person, like let's say I pull up, everyone's like, oh, 30 years old, 32 years old, 31 years old. And then I get someone who's like 80, right? In my sample, okay? And I have like that mean, right? It's gonna pull over to that 80 person, right? How confident can I say really about what my mean is gonna be to the population? Do I think that's gonna be accurate or do I not think?
Not as accurate because it'll be skewed by the outlier.
Yeah, so there's definitely something about that outlier. It's like, that seems untypical. Like maybe just by happen chance. It's more likely that I pulled the more frequently people, right? Because remember in that bell curve, assuming bell curve or whatever, but I'm most likely to pull the most frequent people at first. And then maybe every once in a while, I'll get someone really weird off to the side, right? And that's kind of the idea of confidence intervals. Like, okay, based on our sample, we can still get an idea of how confident our mean is going to be and how big our spread is. So we know we're probably not going to get it exactly right, but we can get an idea of a range, okay? And that's what our confidence interval pulls up, right? Does that make sense to people? Give me a thumbs up if that's, okay. I think that logic holds pretty good. All right, so this is where I'm going to say about like how we talk about confidence intervals, because I will tell you statistics in particular is very like easy to accidentally phrase in the wrong way. So this is actually very similar to the curriculum. If I say something like we found our 95% confidence interval for ages to be from 26.3 to 28.3. Okay, whatever that means, like, okay, 95% confidence interval. Or we can say like, we are 95% confident that the average age falls between 26.3, 28.3. Now these might look very similar to each other, but note that this one actually is technically the incorrect way you should phrase this. And people will honestly, people will phrase this very frequently in this way because it sounds more correct, right? But this is actually the more accurate version, where we're basically saying we have a 95% confidence interval for ages to be from 26.3 to 28.3. So kind of just re-emphasizing the incorrect way, right? There's a 95% probability that the mean age is between 26.3 and 28.3. So there's some notion of saying, you know, like, oh, like the population must be between this part with a 95% probability. That's not quite correct. What the real interpretation should be is like, if we find 100 random samples and create confidence intervals, we expect 95 of those intervals to contain the true population mean. Okay, so it's a subtle difference, but it's an important difference. It doesn't mean that you are likely to have the mean, the true population mean in your confidence interval. It just means you are one of many possible samples you could have created, like confidence intervals. And there's a 95% chance that most, like 95% of all my confidence intervals I could have created, that I'll land in here. And so that's kind of like how confidence intervals are interpreted. But it means that we can kind of think of it as like, okay, like we can get a good idea. It's like 95% confidence interval probably means like, you know, only 5% of the time we won't capture, you know, sometimes we call like capture the population mean. Make sense? I know the words kind of can be a little confusing, to be quite honest, but I just want to make this distinction. But this is the correct interpretation of how you should think of confidence intervals. So I wanted to show you guys a little bit about like, I can honestly, making confidence intervals is like super easy. Like you can basically use a statistical package and say, hey, here's my sample, find my confidence interval. And it feels like black magic. It's like, cool, like how did that happen? So I'm gonna kind of walk you through parts of this, of like how we actually build up this confidence interval. So I think this is kind of helpful to get an idea of like where this comes from. So I have a little bit of code here. So let's just start with basically importing NumPy and Pandas. So I use the Pandas here because I'm actually going to use the Titanic data, right? So this Titanic data is pretty useful. I'm just going to play around with. And I'm getting the ages like we did last time. And just to kind of show you guys, like, okay, we got this data. So remember, if we have, let's see, how big is this? Len of ages. I think it's like 700. Yeah, 700 people with any null values. And we can see here, like ages, if let's do np.min. Right, and let's do np.max ages. You can see here, it goes from, I don't even know what 0.42 is, but like whatever that number is, so like less than 1 year old all the way to 80 years old, right? And then if I wanted to, I can also check out like np.standard deviation of ages, right? You can say, okay, 14, so there's a spread of 14, stuff like this. I can also plot this out, right? So I could do, oh, I don't actually have this. I'm gonna move this guy up so we can plot him out. So I can also plot this guy out. So let's just do, oops. So tell me how should I plot this values out? So I can kind of just check out what the distribution looks like based on my code values. Yeah, so tell me how I could write this histogram. There's a few ways, so.
Plot.hist ages.
All right, just like that. Oops. I spelled it wrong now. There we go. Let's try that. All right, awesome. So there we go. We got a nice histogram. We could have also done a few other things too. I really like the displot from Seaborn. So this creates a nice KDE and stuff like that. So you can see the histogram here, but they're both valid ways. We could have also used the Pandas data frame, but you can kind of see a little, you know, how this difference. It's like, okay, there's a huge spike right here. So a bunch of people are pretty young. And then we have this main spike and then it kind of tails off over to like 80 years old. Okay, so now we can actually build up like a sample. So one way we can sample is actually take our ages. Remember, age is just a series, right? And then we can sample. This is just what's it called? Built into Pandas. And I can say, okay, our sample, we're gonna pull up 10 different people. So you can see 10 or n equals none. Basically, we're just saying, okay, pull up 10 people. We also could have done it fractions, like a fraction number of it. And then we're going to do replace equals true. So note that by default in pandas, if someone asked about sample versus np.choice, well, random.choice, replace is always set to false by default in pandas, where in NumPy we'll see it's actually set to true. So I'm going to actually replace it. That way I can pick the same person twice. We'll see why this is important later. But if I do the sample now, pull 10 random people, and you can see here I got 26, 22, and what's nice about, because it's a series, I actually see what ID they are. So I can actually see if I pull the same person twice or whatnot. So this kind of gives us a good range. And if I actually try this, well, it's going to be a different one now. But if I do mean, and let's actually display sample. And you can see here, we have a mean of 34.7, which we saw before. Does anyone remember what the mean was overall for this population? It's like 28-ish, I think. Maybe 29, something, 27, 28, 29, something around there. I guess I could have just done like this. Ages, oops, not mean, right? So looks like 29.699. So about 27 or 26.7. Okay, or sorry, 29.7, there we go. So that's how we can kind of say, okay, our sample's pretty close, like not far off, right? But we're gonna assume that we don't know the actual population, right? How can we kind of build this up? So to kind of motivate this question, like it's like, okay, what tools will we need? We're actually going to build up this little function here. So I made this function called get all sample means, super creatively named. I'm going to pull in data. I'm going to say n is saying how many we're going to build up a sample. And then just let's pretend we do 100 samples, however many samples we do. So a sample of 10 and do that 100 times. Okay. And then what I'm going to basically say, pull up all these means. So if I do this, this is kind of like what we did before. I'm going to do this 10 to the power of 3. Which is 1,000, yes, 1,000 times. So I'm gonna basically pull up 10 people randomly from the ages group and then calculate their mean and then do this 1,000 times and then see, what we got. So we can see samples. If I quickly just show what are samples, you'll see basically that there's a whole bunch of people and you can see, let's see if I can find this right. Oop, I actually think I wrote this wrong. Did I write this wrong? Sorry, I'm thinking through real quick. Why does this look wrong? This should be n equals 10. Let's do something simple so I know. I know it worked, so let's see. Okay, so this is wrong. What's going on? This is why live coding is always awful. So I'm reading this through. Let's try to just go from here.
Is it the n equals 10 on the input or no? Like on the input?
You're talking about this guy? This guy? Yeah, I think something's going up on here. I'm trying to think. Oh, I'm sorry. This is returning the means, right? So I forgot. It's sampling 10 people. Oops. It's sampling 10 people and then calculating the mean for that. So I'll kind of, I've confused myself. So if I were to recopy this guy, do you guys see what I'm talking about though? Probably not. I see a couple nods, other faces like I'm not sure. So if I do like, let's say 5 samples, right? And n is 10, we're doing 5 samples and then we're pulling up 10 people at a time. You should see, oh, data is ages. You can see here is that I'm pulling 5 samples. So each row is a sample, but each time I do a sample, I'm doing 10 people. Does that make sense? Okay, so with that then I can say, okay, do an np.mean. And the reason why I can do this is that if I just do np.mean here, that's gonna average everyone together. And you can see, oh, that's not what I want. I want the mean for each sample I have, right? So instead, what I can do instead is just say, okay, I wanna do this, but I wanna do the mean across each row. Well, row is axis equals 1. That's always confusing, but trust me that axis equals 1 is the row. And now I can have a mean for each sample. So I should have 5 samples. So I have a mean for each of those samples. Everyone see that? Cool. All right, see, I confused myself, which is why you shouldn't do what I did, which is leave a comment there, but not actually say anything. So it's always useful to document your stuff. So when you look back to it, and I wrote this like literally like 20 minutes ago. So like you can see already that I'm not even following my own advice. But if I do this now we can see, like, for example, if I do samples, you'll see that there should be 2 of them because there's 2 samples. So again, going back to 1,000 samples, 1,000 sounds like a nice one. You can see how many there are. Make it small, right? And I can go ahead and plot this out. So I'm going to plot out this guy right here using Seaborn. This is going to plot out, what have ages? That's probably not good. I think that's, well, let's see. Past Victor does things and he doesn't know what he did. All right, so I'm going to do a distribution plot of these samples. So like all these sample means. Notice KDE saying false, hist false, rug. I don't actually know what rug stands for, but what rug does is it shows us a little plot points. It basically shows like where those points happen. So you can see these are all the different sample means. So what I did here is I'm putting also, if I run this guy, you can see this is the standard deviation, or this is the distribution of the population. This is the true population's mean, and we're going to see how this compares over here. So if I run this guy now, you can see I put them all together where you can see it plots in orange, so that way it's not the same color. And you can see here, there's my actual population, and this guy, basically it's all centered around here. So you can already see it's very close together. From my random samples that I grabbed, I still get very close. So this is what kind of we saw with central limit theorem. Like, okay, like, so we see this kind of works. So now you say, okay, Victor, like, cool, you made some fun functions, you know, awesome. But how does this relate to confidence intervals? So what a confidence interval really is about is saying if we were to resample on just our original sample, it's going to get kind of meta. So we take our sample, we get 10 people, and we say, okay, what if we just resample over those 10 people? And we do this over and over and over again, okay? What, first of all, what should be the mean, what should be the, if I took the mean of all of those resamples, what should be the shape be? How should it be distributed?
Normally.
Normal, right? It's like whenever someone kind of gives you that kind of thing in statistics, it's like, it's normal, right? It's almost always, right? It's kind of like someone says, what's the answer? It's usually either 0 or 1. That's kind of a little joke with that stuff. But yeah, it should be normal. So what we can think is like, okay, our confidence interval, we can say how many of our sample over, how many of those samples actually cover the percent of like all the different ones. So we'll make an interval of saying, all right, we have like this sample mean, this sample mean, this sample mean, this sample mean. What percent is actually being covered? So if we say 95% of them are covered, that would be our 95% confidence interval surrounding that area. So I think, honestly, I don't think I explained that the best way. So I think I'll draw it out for you guys real quick because I think that's helpful before I go into code. Is that imagine we have, remember, just our sample of 10 people, and I just resample over that. And I say, okay, like I resample over that sample, my resample mean is right here. And then I resample again, my sample of that is over here. Resample again, right here, right here, right here, right here. And like I do this over and over and over and over again. We'll get something like a normal curve. And then what we say, okay, our confidence interval, we'll say the average, like like when we first sampled, so our first sample, before we resampled, first sample mean. That's what we're going to talk about saying, oh, that's our estimate of the population. But then we say, well, how, what's our confidence interval? Our confidence interval is saying, well, okay, if we have a 95% confidence interval, that means 95% of the different resamplings will be found within this interval. So this interval going from like, let's just say 27 to 28. Okay, I'm making up these numbers, obviously, but that would be kind of like saying, oh, that's our confidence interval. And the reason why we can do that is because, hey, remember the central limit theorem? If we resample a bunch of times on a sample, we can build a normal curve. So because we're building a normal curve, we know exactly how to calculate this value right here. Like it's actually really easy for us to do computationally. So that's the whole point of like, so why we're able to actually use a central limit theorem for confidence intervals. That's how they connect. Does that give me a thumbs up if that made sense? Thumbs are sideways. You're like, I'm still thumbs down if you're like I don't know what you're talking about. I think I'm seeing thumbs up mostly, and either not faces or frozen screens. So I think I'm seeing most people getting it. So okay, so like, how do you implement this? Imagine like, okay, we don't have fancy tools. How do we do this actually in the code itself? All right. So this is, when I said we do a sample of samples, so like we have our sample and then we resample over and over and over again, this is something called Bootstrap. So I think this is actually in section 15, technically, when they talk about Bootstrap versus Jackknife. Just for the record, most of the time we'll talk about Bootstrap. But basically what Bootstrapping
it's the
does,
last bit of 14. I'm just
last bit of
right
14?
now.
Perfect.
Yeah.
Oh, good. We're on 14 then. Perfect. It got moved around a little bit, so I always get a little lost. But Bootstrap basically means that we're resampling on our sample already. So like you ever hear like pull yourself up by your bootstraps, right? Like you guys heard that term and stuff. We're basically using something I already have and using it over and over again to get a new thing, which is kind of cool. So this Bootstrap little function I made, it's going to pull in a sample. So it's like, all right, here's your sample of 10 people, for example. I'm saying sample and example too many times, but you have 10 people in your sample. And then you say, all right, we're going to resample. In this case, I put default 10,000 times. We're going to resample and basically pull, like you can imagine your sample is like names in a hat, right? And you pull out a name, you write it down, put it back in, you write it, pull another one, write it down, put it back, and you do that, right? So many times. So then we record each of those means because we're trying to get the central limit theorem here. And so this BS sample means is going to basically use that get all samples. See how I made that thing before? Get all sample means. We're going to pull in the sample. And note that this n is the length of sample. So that way, what we have, if we have original sample of 10 people, we're going to resample from the sample 10 times, right? Or like you should resample with 10 different, not 10 different. I'm trying to get my brain all mixed up. If you imagine we have our hat, right? I'm going to draw it because that's going to make it easier for me to have something consistent. We have our hat of names. That's our sample. And then we have our list right here. This is our bootstrap. I'll call it boot. Okay. So our first one on the list, we basically take our name from the hat, look at it, write it down, you know, like age number, put it back in, pull it back out, get a new name, put it back in, write it out. And we do this, in this case, if the sample is a size of capital N, we do this so each bootstrap sample is N, large. Okay, so we will definitely, like, we likely will get repeated values, right? Because we're going to go over and over. It's possible we get a different value every single time, but most likely we're going to get repeated values because, right, that just makes sense. And we do this for, in this case, 10,000 times, but it's just some large number essentially. Okay, and this allows us to do the central limit theorem. Okay, and so if we then take, say, all these means here, we're going to get 10,000 different averages, 10,000 different means. We can then say, okay, but now this has a normal curve. What does 95% of those means cover or are covered under? If I'm not losing anyone too much. Is this making sense? Thumbs up? Okay, good. Oh, good. All right. Or you guys are just nice, I don't know. So we're gonna go ahead and do our sample, right? And so just really quickly remember our sample, just to kind of show you what that looked like. It's just 10 people, right? And so you can imagine this is kind of, you know, this is a completely random sample. We have no clue, you know, like if it's actually representative of the population, right? In fact, if I do, let's do np.mean, the sample is 30, which we actually know for a fact, it's like, oh, it's a little bit bigger than what it should be. But we want to say, okay, what's our confidence interval? So now I'm going to write my bootstrap sample. So I put b sample means. So now I have all the means of this sample. I'm going to go ahead and plot this out just to show you, and then also the mean of that bootstrap sample. And look at that beautiful curve. Like you should be like, your heart should be fluttering right now and fall in love with this normal curve because it's like, yes, we can do real cool math, right? And so once we have this guy, we can say, okay, cool. Like we actually know like where the mean is, right, of this bootstrap sample. In fact, let's go ahead and write that down. So b sample, oops, np.mean, the mean of mean. So we can use 30.37, right? Which should be close to our original sample size thing. So that's why we're gonna actually use that sample or like that mean as like, oh, this is our base. And we say plus or minus, you know, so much. Like if you ever hear like plus or minus this percentage or plus or minus the standard deviation. So we can then calculate, you know, let's say we say, okay, if we can figure out the area underneath this curve right here. Okay, let's say, oh, we want 95% of all the values to be in whatever this value from here to here is. We can actually figure that out because how many standard deviations is 95% under a normal curve? 2, right? Yeah, good. So we have 68, the 95, and then 99. technically 0.7. And my handwriting's awful. 68, 95, and 99. This is 1 standard deviation. This is 2 standard deviations. This is 3 standard deviations. So if we want a 99% confidence interval, we just have to go 3 standard deviations from this mean, right? And then we know, for okay, we go 1 standard deviation, 2 standard deviations, 3 standard deviations. You're like, oh, that's what it is. So just to kind of show you how you would do this numerically, and I think this is useful to like show you like, you know, how we would do this. We can do NP dot, how do we find standard deviation with NumPy? I guess it starts with S.
The STD, right?
STD, right? Standard deviation. And we can see here, it's like we take the value right here, the sample. We're not gonna worry about axis because it's just one value, right? Or set of samples. So B sample, and our standard deviation is 4.89, okay? So that means if we want 2 standard deviations, right? So let's say a 25 or 95% confidence interval, we multiply this by 2. So that means our confidence interval, I'm gonna say this is 2 STD equals this. Our confidence interval then should be, let's call this the B mean. Or I guess we have our sample, right? So let's do NP dot mean of sample, right? Minus 2 standard deviations. And then all the way to NP dot mean sample plus 2 standard deviations, okay? And so this is our range right here. This is our 95% confidence interval. Check that out. We didn't have to do any fancy package. We just used good old NumPy, some pandas, Victor talking a whole lot and messing up words constantly. But you now have like, and you can see that kind of makes sense. You can kind of see about 95%, it's about 20 to 40 right there. So not bad. And what's really cool is that we can actually, you know, we can do whatever percentage it is. Now, obviously, this makes it a little bit more difficult because then you have to figure out the normal curve and do that. But that's what packages are for. We can say, oh, I want a 92% confidence interval. You can just pass it in there and it knows the shape of a normal curve and it can figure that out. But this is how the motivation of where this comes from. I'm trying to clear my annotations. There we go. Cool. This is where like I showed you a whole bunch of stuff and we skipped over. This is where I think the curriculum kind of shows like you can use scipy.stats. And we can say, okay, let's do the actual normal curve right here. We can say a CDF, right? Because remember, our normal curve goes up this way. So we say, what was it, 20 to, let's say 40. And that should be about 95%. And there you go, 95%. So, oh, I guess technically, I did this like, it should be the same thing, but it should be from 40 to 20, right? So you can see, understandable. Since we could see, you know, standard deviation is about, what was it? What's the standard deviation? 14, right? Is that right? 14? Let's see. 2 standard deviation. There we go. Oh, nope, I was wrong. 9.7. So let's say about minus 10, right? So let's say, okay, from 30 to 10. All right. Oh, wait. Oh, that's hard to do because it's that's closer in size. All right, I'm gonna leave that on. But you could figure out the next 2 standard deviations, right? Oh, that's 2. Victor can't do math, there we go. So 40 minus 4.9, and then 20 plus 4.9. We should get about 65, so 90, or 70%. So you can get the idea there, like how you can build this up. Okay, does that sound pretty good? Give a little more like, I feel it gives it more context of like what this confidence interval is. In reality, you probably will not do this. I know that kind of like did a whole bunch of things, but I think it's useful to be like, hey, this is what this confidence interval comes from versus like saying, oh, here's the package, just run this. Now you can kind of be like, okay, I can see where this comes from. Any questions at all for this guy? No, feeling pretty good? Awesome.